So hello friends, my name is Kamal and I welcome you all to my YouTube channel, and please like, share, comment and subscribe to my channel. Today I'll discuss one important topic from the EPR, electron paramagnetic resonance. So when you see EPR spectrum, for example, of axial system, example copper, elongated copper, what you see, you observe that there are two types of G. Normally we call it G parallel and G perpendicular, and the observation is that the intensity of the G perpendicular peak is very high compared to the G parallel. Now what is the reason behind it? Why the G parallel peak is having low intensity while the G perpendicular have a more intensity? So today I'll discuss about that and try to understand why these things happen. Now before discussing about the axial system, let me just tell you quickly about the isotropic system. In isotropic system, all the directions are same, so Gx and Gy, Gz. So for example, you can think of a sphere. So in sphere, you have all the directions are same. You cannot decide which one is Z, which one is X, which one is Y. So you can randomly choose any direction as that direction, then you can fix X and Y. Now in axial system, you have a choice. So so the point is that how to decide that choice. The choice is given by the group theory. Now in group theory, you can, if you have a molecule and you see that the molecule has a principal axis of symmetry, and then that axis is known as z-axis. That axis is defined as a z-axis. If you have a molecule where you have more than one principal axis, then suppose two symmetry axes are there, then you have to choose the highest principal symmetry axis as your z-axis. Now, once you choose the z-axis, your next target is to choose the x and y-axis, because we know x and y has to be perpendicular to the z-axis. Now, what I have drawn here, I have drawn an ellipsoid. So this is a representation of an axial system. Now you can see this axis which I'm showing in the blue color is my z-axis. This I have chosen from the theory. Now the problem with choosing x and y is that I have infinite possibilities. Okay, now to explain this in more detail, just I have cut a portion, circular portion from this region, and you can see here, this is the z-axis which we are talking about, and then you can see I can choose x-axis in an infinite way. I can choose this one as my x-axis, this one as my x-axis, this one as my x-axis, and also this one as my x-axis. So there is no unique way I can choose x-axis. So I have infinite possibilities out there. Now because of this, in your actual EPR spectrum, so you have more probabilities of molecule in be in a perpendicular direction compared to the parallel direction. Now the parallel or perpendicular I'm describing in terms of the laboratory axis. So in the laboratory axis means the instrument axis. So in the instrument axis I have a direction along which I have applied the field. So I can choose this axis as my z-axis. Now if the z-axis of the molecule is parallel to the laboratory axis, then it is G parallel. Now if the z-axis of the molecule is perpendicular to the laboratory axis, then these are known as perpendicular axis. Okay, so we'll associate G values for them G perpendicular. Okay, so this is the origin why the intensity of G parallel is lower than G perpendicular, because very less number of way I can decide the G parallel, but there are infinite or more ways by which I can decide the X and Y axis. Let us look at the actual experimental thing. What happened in the experiment? Now, suppose this is my solution, and so in the solution, the molecules may orient in any direction, and there is very difficult to control. I cannot decide which molecule will orient in which way. So they will decide by themselves, and there are all possible orientations exist. Fine. Now, because of this, when you do an EPR experiment and see the absorption spectrum, that spectrum will be very broad. Okay, this picture I have taken from the book called Drago. You can see the absorption spectrum is very broad, and all possible, all peaks, this graph represents that all possible orientations exist, and I can get a resonance for all possible orientation. But the problem is that it is very difficult to interpret this kind of spectrum. So mathematics help us in this, in solving this problem. Now, if we do derivative, you do not see any other intermediate peaks except the G perpendicular peak and the G parallel peak. All the peaks you are not able to see in the derivative spectrum. So it is a derivative spectrum, because of which I am not able to see all other peaks corresponding to different orientation. But if you do, and if you convert this spectrum to the absorption spectrum, that means if you integrate again, so you should be able to see all the peaks. Now, if you want to see a G value for a particular orientation, and you just give the theta value of that orientation. Okay, what is the angle between the G Z of the molecular axis with respect to the laboratory axis? Then you should be able to get the G value of for that particular orientation. But in in the spectra we normally read in EPR spectrum, we do not see anything because it's only because of derivative. Okay, but in reality, all possible peaks are there. So as I said, because many possible orientations are possible for X and Y, I can draw. I have many ways I can draw X and Y, but there is very less number of way I can draw for Z. Because of this, the intensity is lower compared to the G perpendicular. So I hope you guys have understood now why the G perpendicular intensity is more compared to G parallel. Still, if you have any doubt, please do not hesitate to ask me any question. So I'll be happy to answer you guys. If you have any problem, any doubt, please comment. And once again, I will just request all of you guys to please share my video and like, comment, and subscribe. Thank you all. Bye bye for now. So I'll come with a new video again. Till then, goodbye.